Okay, welcome to Lecture 2 of Statics. This is vector addition using components. Basically we're going to kind of do what we did last time. So there will be a little bit of review there because I'm going to do it kind of using the triangle or the parallelogram method or whatever they want to call it, tip to tail or whatever. And then I'm going to do it again. I'm going to do the same sort of problem, but I'm going to do it using components. You'll understand what I mean when we get there. And then we're going to start basically using that to kind of get at a force equilibrium. And then the last thing I want to do here, and I've kind of left it in red because it's really going to depend on how much time we have, is I'm going to introduce 3D. Okay, if I don't have time for 3D today, then I'll just kind of make it into the next lecture. Okay, so what I want to do is I want to start with quote-unquote a typical problem. And we worked one like this last class. And the typical problem is, they always, the ubiquitous they who makes us do all these problems. There's always a, well, let me see if I can get a little pen here so I can actually, there's always a loop or something. And attached to it is two ropes. And the ropes can go at all kinds of crazy angles. In this case, I've got one going off at 30 degrees from the horizontal and the other one going off at 80 degrees from the horizontal. So 50 degrees up from that. And the question is, what is the resultant here? Okay, so basically, if I were to replace these two ropes with a single rope, what would its effect be? Now, you can imagine, of course, that, I'll kind of do this in white, but you can imagine that it's going to be somewhere off in this direction. I suppose part of this typical problem is we need forces on these ropes. So let's make this one 10 newtons, and let's make this one... 7 newtons, why not, okay? And so, you can see from that right up, the 10 Newton one is more important than the 7 Newton one because its magnitude is greater. But, we don't really, it's a little tricky here, right? What is the resultant of these two forces? And so the first thing I'm going to do here is I'm going to label these forces because I want names for them, right? So this is going to be force A, and this will be force B. Okay, just because that's going to make it easier for me. Okay, these are vector quantities, so I put the little line over them. So the solution here, so given is everything shown, and the required is I want the resultant. And then the solution is R equals A plus B. Okay, now if we do this the way we did this in last class, there's going to be a lot of trig involved here. And so first I'm going to draw these things, and then what I'm going to do, and I didn't do this last class, but it's something that I always like to do if I can remember to do it, is just kind of think about the tools that I have to work with, the trig tools. So first, let's kind of diagram what's going on here. So the first thing is I've got one force, okay, going off like this, and that's A. Okay. Now I need to do tip to tail and put B on there as well. So B is going up like that. Okay, so that's really inconvenient. Okay, but this is what happens if I add A to B or if I add B to A, because I could also have done this. I'm going to do this and then probably erase it, but I also could have started with B, kind of off this way, and then added A, going like this. So I could have done B and then A if I wanted to. Okay, that also would have worked. This is often, well, if I'd drawn it right, this would be a parallelogram. And a lot of people call this a parallelogram rule. I don't really care what name it has. Anyway, regardless of whether or not you add B to A or A to B, we end up with a triangle. Okay, because the resultant then is this, that's kind of what we're looking for here. And the resultant is coming from here all the way up to there. Okay, so this is going to be the resultant that we're looking for, and that is not supposed to be a B. That is just bad handwriting. Okay. Anyway, so there's the resultant. And now our goals here is to figure out what the resultant is. And so we know a few things on this triangle that we can label, right? We know A is 10 newtons. We know B is 7 newtons. After that, we're really going to have to get into the geometry of this thing. And so the first thing we can do here is I could say, well, look, this angle right here, that's 30 degrees. Okay, that seems pretty straightforward. This angle right here, from the horizontal, okay, so that's from the, these are both from the horizontal. This angle right here from the horizontal is, well, if I look back over my other drawing right here, okay, it's 80 degrees. Okay, it looks like it's a right angle, but it's not quite. Okay, so now we're left with, okay, so this thing, if I continue this line going this way, I'm kind of stuck, aren't I, right? Like, I'm going to have to start getting into some serious trigonometry in order to figure this out, okay? And, you know, the best thing to get here would be if I could get, hold on a second, let me move that A because it's kind of in the way. I did not want to highlight that A. I wanted to delete it because it's right in the way here. Okay, so let's go ahead and, you know, move my label for A to right here. Okay, is, you know, I want to start thinking about if I can get this whole angle here. Okay, now that may not be obvious to you that we need that whole angle, but let's just kind of, let's do a little aside here. We'll go right up in here, and I will write in white here, we're gonna do our trig tools, okay, our tools. Okay, and these are gonna be for trig, really. And so the first thing I'm gonna do is I'm just gonna, so there's basically 4 tools that we're gonna use again and again and again for trig. And some of them that work for any triangle. Okay, and the first one of those is the law of sines. Okay, so the law of sines. And of course, anywhere where there's a law of sines, there is a law of cosines. Okay, and these work for any triangle. Okay, and the way that we're going to think about this, any triangle, is the way that I typically have always seen this done. So this is just a random triangle. So this is side, well, I don't want to use the letters I used earlier, so we'll use lowercase letters, A, B, and C. And then across from A is angle alpha, across from B is angle beta, and across from C is angle gamma. Okay, so this is typically how it's done. So the law of sines here helps me out, basically, if I own, you know, if I know a side and an angle that are across from each other, then as long as I know one more thing in this triangle, I can figure everything else out. Okay, so it looks like this: A over sine alpha equals B over sine beta equals C over sine gamma. Okay, and this this really is 2 equations, or even 3, depending on how you define it. Okay. You know, so basically, if you knew A over sine of alpha, so you knew A and you knew alpha, then you could set that equal to B over sine beta and solve for whatever you need. Or you could set A over sine alpha equal to C over sine gamma. Okay, however you want to do it. Okay, the law of cosines, on the other hand, looks like this. It looks like C equals the square root of A squared plus B squared minus 2AB cosine gamma. Okay, and we'll extend that line this way. Okay. Cool thing about this one, or the interesting thing about this one, is that A, B, gamma. A, B, gamma. Okay, notice that if we can get a side and an angle and a side, if we can get them all next to each other, then we can use this. Okay, so your goal here is to get 2 sides around a single angle. And that will be, and then you can use this. The other thing that I note about this is that if you pay attention to this, you'll see that C equals the square root of A squared plus B squared. The first bit of this is the Pythagorean Theorem, okay, which you already know, but normally you use that for a right triangle. This would work in that case if gamma were 90 degrees. Okay, if I put in 90 right here, then the cosine of 90 is 0, and this whole thing goes away, and you get the Pythagorean Theorem. Okay, so the Pythagorean Theorem is really a special case of the law of cosines. Okay, so those are some of our tools. The other tools really are for right triangles. Okay, and so the strongest, so, you know, here's our right triangle, I guess. Right triangle. Okay, boom. give it a right-hand side. We got A, we got B, we got C. Okay, we've got angles here. Yeah, so I could call these angles whatever I want. Let's call this one beta. Let's call this one alpha. Okay, to kind of keep with our notation up there. So A is across from alpha, B is across from beta. And you should already know these. So the first one is Sohcahtoa, okay, which I never learned Sohcahtoa, or at least I never learned it that way. So in this case, the sine of an angle, let's pick beta, okay, equals the opposite of beta, B, over the hypotenuse. So that's the opposite over the hypotenuse, which is C. Okay, the cosine of beta is going to be the adjacent angle to beta, which is A, over the hypotenuse, which is C. Okay, the tangent of beta, okay, so now we're at beta. We need the opposite, which is B, over the adjacent, which is A. Okay, similarly, we could do this for alpha. So we could do, well, not tangent. Well, we could do tangent, but let's kind of keep this organized. So we could do the sine of alpha equals, so now we're, in alpha territory. So the opposite, so we're going to go opposite over hypotenuse. So the opposite from alpha is A, and the hypotenuse remains C. Okay, and then we do the sine of alpha, cosine of alpha. Cosine of alpha, okay? And now we need the adjacent over the hypotenuse. So for alpha, the adjacent is B over C. And then for tangent of alpha, okay? So then it's going to be the opposite over the adjacent, so A over B, okay? So that's Sohcahtoa. So yes, you should be able to do that. You should know that. It should be a review. Now, if it's not, it's okay. There's no shame in that. But let's make sure we know how to do it, okay? Because we're going to have to be able to do that. Okay, and then the last part of the Trig Tools is going to be basically the special case here, where we have a right triangle, which is a squared plus b squared equals c squared. Okay, so that's Pythagorean Theorem. Okay, so those are our Trig Tools. Okay, so when I'm up there and I'm looking and I say, like, for example, for the law of cosines, I want a side, an angle, and a side. I'm saying that because I'm over here and I'm staring at this thing and I'm like, look at this pretty problem, right? I've got a side, I've got a side. All I need is this angle right here, and the world becomes a better place. Okay, so now we're going to use a little geometry to kind of get at that. So first I've got this 30-degree angle here, okay, and I've got a line here, and I've got another line that's parallel to that. So this portion of that, I think they call these alternate interior angles. This one is also 30 degrees. Okay, so now I've got if I draw a little vertical line right here, okay, that means this whole thing between these two axes is 90. 80 of them are already taken up right here. Okay, so now we've got a little 10 degrees right in there. 10 degrees right in there. Okay, and then between those two axes, then this is a right angle right here. Okay, so I've got 90 there. So if I add up all three of those angles, this entire angle here becomes 30 plus 90 plus 10. So 130 degrees. Okay, so now that I've done that, I can use this law of sines, or excuse me, law of cosines, which I'm having trouble getting onto the screen right now, and I can solve for r. Okay, so what is the law of cosines? Let's see here. So that is going to be, so generally it looks like this. However, I'm going to write it for my particular case, which is going to be that the magnitude of r equals the square root of one side, 10 newtons, squared, plus the other side, which is 7 newtons, squared minus 2 times 10 newtons times 7 newtons times the cosine of 130 degrees. Okay, the angle between those two sides. Okay, so we can plug all that nonsense into a calculator. Okay, and we end up with 15.459 newtons. Okay, I always recommend you keep 5 sig figs throughout your problem. Okay, that's just my recommendation. Okay, so that's cool. Now for the second half of this, we need to get this angle. Okay, the angle from the horizontal. Okay, because we're looking for a vector. We're not looking for just the magnitude of the vector. We want the whole vector. So we want to get this little red angle. If I can get that little angle down in there, okay, if I can get this little angle right in here, okay, if I get that angle, then I can just add 30 to it, and that's how much the angle is coming off of the horizontal. Well, the nice thing is at this point, as I said, probably the most useful thing in triangles is the law of sines. So we can apply the law of sines, which I'll do, maybe I'll do right in here, and I'll just kind of zoom in real close so there's plenty of space. It's kind of nice to be able to zoom in. Okay, and so for this particular situation, I'm going to start with, well, I know the resultant, and I know the angle across from the resultant. So the resultant is, well, we just solved for it, 15.459. 15.459 newtons. Okay, divided by the sine of the angle across from it, 130 degrees, equals. Now all I have to do for the other side of the law of sines is pick an angle and a side that are across from each other that I want. Okay, and in this case, I want the little red angle, and the side across from it is 7 newtons. So I'll do 7 newtons times the sine of the little red angle. Okay, there should be a kid's book called The Little Red Angle. So anyway, so then if we solve this problem, then what's going to happen is I'm going to end up with alpha, the little red angle, equals the inverse sine of 7 newtons divided by 15.459 newtons times the sine of 130, okay, which technically is on the top of that thing. So if we do this, alpha equals 20.296 degrees, which means that R, if we write this all out, we get R equals, and we don't only have those absolute value brackets because I'm going to put a direction, 15.459 newtons, and I'm going to give it an angle, which is not that 20. We have to add this other little 30, so we're going to say at 50.296 degrees. And now you might be saying, well, that's awful lot of significant figures, and you're exactly right. So I don't want to report it that way. I want to round to 3. So we want to keep 5 all through the problem, but then we're going to report 3. So this will be 15.5 newtons at an angle of 50.3 degrees. Okay, so that is, in a nutshell, kind of how we did it last class. Okay, and it does not like my fingers right now. Okay, so that's a lot of work, and there's nothing wrong with that. And it's pretty cool because, all that trig that you learned, you start to see like, oh, look, there's an actual purpose for it. And so what we're going to do now is we're going to do this again. We're going to do this slightly differently. Okay, this time we're going to add vectors using components. Okay, so here's our typical problem. Of course, I have to, give it those sides again. We're going to note that we're going to get the same answer this way. And then I'll explain, to some extent, you're going to want to do it whatever way makes it easiest for you. But that's not really going to work. Okay, so I'm going to, we'll talk about that in a second. So, and again, there'll be I'm going to do a little teaching on the way here. So, again, so the resultant, just like the last time, the resultant equals A plus B. Okay, just like last time. And you could do B plus A or A plus B, whatever it is you want to do. But what we want to do here instead is we're going to kind of think about this in a different way. So what I want to do is I want to just look at this A vector, okay, and I'm going to look at it like this, okay. So let's imagine this is the same drawing as it was before, okay, and it's 10 newtons, whatever. And what we want to do is, instead of just thinking about the a vector by itself, we want to split it into two other vectors. Okay, and these vectors are going to be ax, okay, with a little arrow, and then there's going to be a y with an arrow. Okay, so sometimes people will write this like this. They'll say, okay, well, a equals ax plus a y. Okay, and that makes sense because if you think about it, walking from, following A, you get to the same place if you do tip to tail, if you go AX, and then you follow that with AY. Okay, so it works out the same way. Now, one of the things that people like to do, and this is another thing that will show up a lot, I think this is the way your textbook does it, is they'll say A equals the magnitude of AX times this little I. Okay, let's zoom in a little bit. Plus the magnitude of the y vector. Oh, yeah, I guess these are times a j. Okay. Or sometimes you will see the same line just written like this: ax times I plus ay times j. Okay, where they just kind of basically say, these magnitudes are kind of canceling out these arrows, right? Okay, so sometimes you'll see it written like that. It's not really important to me which way you write it, but you better be consistent if there's points writing on it. And so what this little I does and what this little j does, and of course if we were to go into the third dimension, it would be a k, so it would be I in the x direction, j in the y direction, and k in the z direction, it is just the number 1 times, it's a vector that has a length of 1 in that direction. So the I direction, I is a vector of length 1 in the x direction. So basically it just says we're going to take all the directionality of this vector and we're just going to put it into that I. Okay, we're going to do the same for j, okay, vector of length 1 in y direction. Okay, and then k, which we won't have in this problem, same 1 in z direction. Okay, so the point of it is just to kind of like make it, well, it'll be clear in a second, but what it does is it makes it so that, because you can imagine that, if you go 10,000 miles to the right, okay, and then you go 10 miles up, okay, 10 this way and 10,000 this way, okay, 10,000 I, 10 j, okay, has adding j made you go any further to the right? It hasn't. Okay, so these two things, because they're at a right angle, they're independent of each other. Okay, so you cannot add these magnitudes. I mean, you can, if you wanted to know how far away you went total, okay, then you can use the Pythagorean Theorem, but this one has no effect on how far you went in that direction. Okay. So these i's and these j's basically keep these terms separate. It's almost like, it's really a bookkeeping thing. And so what we're going to do now is that by doing this, we can then further this, okay, because we know something about triangles. Okay, and so we can use whatever angle we want here. It is typical to use the angle with the horizontal, but it doesn't have to be that way. So I'll call this angle theta. And because we know trig, okay, I'm going to go down here and I'm going to do some Sohcahtoa. Okay, because I don't want to be dealing with ax and ay. Okay, so what we're going to do here is I'm going to say, okay, well, Sohcahtoa, right? I want to get at what ax is. So ax relative to theta is the adjacent, right? So that means Sohca, I need to use cosine. So the cosine of theta equals the adjacent, which in this case is ax, over the hypotenuse, which in this case is a, like that. okay, which means I can say pretty clearly or pretty unambiguously that if I cross multiply here, that AX equals, or at least really these are the magnitudes of these things. So AX equals A. Whoop. Oh, that is really ugly. Okay, let's erase that. Is A times the cosine of the angle. Cool. All right. Now I want to know what AY is. So AY, okay, well, relative to that angle, it's the opposite. And I'm going to use the opposite of the hypotenuse. Okay. So we'll go down here and we'll say, so that the opposite of the hypotenuse is the sine. Right? Sine of theta equals the opposite, which is AY, like this, the magnitude of that, divided by A, the magnitude of that. Okay, so if we rearrange that, I can say that the A of Y equals the magnitude of A times the sine of theta. Okay, so this is pretty cool. Okay, so what I can do is I can go back over here, right up here like that. Okay, and I can plug in up here. Okay, and I can say A equals, so for AX, I'm going to have A, the magnitude of A. How do we put that? Let's do it like that. Times the cosine of theta times I, plus the magnitude of A times the sine of theta times J. All right, so that was a lot of noise. That's a lot of noise. Okay, we just did a lot of stuff. Okay, so that's a lot of things. All right, now I'm going to this is almost going to be more algebraic than the last one. But what I've done here, just to recap real quick, is I took my A vector, which is like this, okay, and I said, you know what? Let's break it down into these two things, okay, that, you know, are equivalent. So we split it apart, and this is what it became. It became this big, long thing. Okay, so now what that means is I can go back over here, and I can split that apart. So I can take A here, and I can rewrite it. Okay, so I can take R equals, do it like this, A, magnitude of A, cosine theta I, plus magnitude of A, sine theta J. Okay, now it looks like we just took a simple problem and made it a lot more complicated. That's definitely true. Definitely true. But what's going to happen is it's going to make some more sense in a second, because we're going to do the same thing to B. Okay? Now, the interesting thing with B, of course, is we're going to have a different angle. So at least for this problem, we could call this one theta, right? And then for B, if we're going to do the same trig that we did over here, okay, this trig, we have to use this angle with the horizontal. Okay, now as a general rule, you can create a different relation than this one, okay, if you use a different angle, okay? And, you know, I recommend that you use different angles. Use whichever angle is easiest, whichever one is given to you, etc. Don't think of this as the rule. Think of Sohcahtoa as the rule, okay? Because you can get whatever relation you want as long as you go back to that. Anyway, so I'm going to do the same thing with B here. So B, okay, I'm going to do it down here, is going to look like this. B cosine theta I. Oh, well, except we're not really working with theta here, are we? Let's make this angle beta. Why not? Yeah, let's do it a little beta. Okay, so we're going to erase that, and we're going to put in a little beta here. Okay, we're going to add B cosine beta times J. Okay, so the key here is what's going to happen is that if I add all of that up, okay, that what ends up happening is this. Okay, these two right here, let me use a different color. These two right here both have i's. Okay, these two both have j's. Okay, so the j's can be combined, the i's can be combined. You cannot add i's to j's, they have to remain separate. Okay, in order to combine i's and j's, you have to use the Pythagorean Theorem because they're at right angles to each other. So what we'll do is we're going to end up with a cosine theta plus b cosine beta, okay, times I. Yeah, so I should note that these unit vectors are sometimes written with arrows and sometimes with little hats, okay, or carrots or whatever they call that. I will probably swing back and forth. I'm used to using the little hats, so I just did a little hat right there. And then we'll do plus b cosine sine, okay, because now we have to do the I side of this thing, okay, sine theta plus, oh, that should have been an A. Ugh, man, I'm really struggling here. Sorry, guys. Okay, so this will be A plus B cosine sine. Man, that's what happens when you erase too much. You start to erase your brain. Will you just erase that, you punk? Nothing wants to erase. This thing is against me. Everybody's against me. All right, well, I'm just going to write over it. Okay, sine beta. Okay, and this is all times j. Okay. Whew. Well, that's really noisy. That's really, 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 really noisy. All right, and of course, it doesn't really help that our final answer then is an annoying answer, right? So let's go ahead and plug in. And you end up with this really long, annoying expression here, okay, which is going to require some evaluation. And all I've done here is just plugged in the numbers, okay? So noting that beta has to be measured from the horizontal in this case, so it's 80 degrees and not the given 50. So if we plug all that in and we solve for it, we get a resultant, which looks like we end up with R equals 9.8758 newtons in the x direction and 11.894 newtons in the y direction. We're going to keep 5 significant figures until we get the answer that we're going to report. Now, this is weird, right? So we've got this answer, and it is weird, right? Because if I compare that to my earlier answer, I got this answer right here. Okay, these are not the same answer, right? Or they don't look the same, or I don't know what's going on here, but they look different, okay? And herein, we end up with a problem here, and this is that the earlier answer up here, this is in polar coordinates, okay? So if you remember from physics, like polar coordinates basically means you got a magnitude and a direction. Easy, nice, okay? Over here, this is what we call Cartesian coordinates. Okay, so basically this is x and y. Okay, we went this far to the right, we went this far up. Okay, nothing wrong with either one of these. However, usually, if you want the resultant, you want it in polar coordinates. This is a lot more logical, at least to me. So what we're going to do now is we're going to do a little bit more of that fancy trig. And so now we're going to say, okay, well, let's look at this. Okay, let's convert this into polar coordinates. And so what we're going to do here is here's my triangle, right? I've got 9.8758 newtons going this way. And I've got, going this way, I've got 11.894 newtons going that way. Okay, and so here's my triangle. And so now I need to know the magnitude of the resultant, which is right here. Right, and I need to know its angle, which we'll call, I don't know, well, let's just call it lowercase r, okay, to go with resultant. Well, it's not really a very good letter for it, is it? Let's give it another letter. Let's give it just a, I don't know, I don't have a good letter. Let's give it a capital W, because, you know, I am Wayne Wagner, and this is my class, and W's are cool. All right, so we'll do this one at a time. So the first thing is we're going to go back to our trig tools. We've got two sides of a right triangle. So when you've got two sides of a right triangle, you want to use the Pythagorean Theorem. So we'll do a squared plus b squared equals c squared. Okay, with a being 9.8758 newtons. Okay, b being 11.894 newtons. And c being the magnitude of r squared. Okay, so if we solve this problem, the magnitude of r comes out to 15.460 newtons, and then the angle then becomes, well, the two sides that I knew the side opposite and I know the side adjacent, so this is a tangent problem. So we're going to say, okay, well, the tangent of angle W equals the opposite, 11.894 newtons, divided by the adjacent, which is 9.8758 newtons. Okay, and so W equals the inverse tangent of that ratio of 11.894 newtons divided by 9.8758 newtons. Okay, so W equals 50.297 degrees. Okay, so we kept at least 5 significant digits through the whole problem, which is annoying because we had to write all these extra significant digits. But now we're going to go ahead and we're going to round. And I'm going to say R equals 15.5, it looks like, newtons at an angle above horizontal of 50.3 degrees. Okay, so we kept 5 all the way through, but we're going to report 3. Okay, and if we go back and we look, okay, up here, it's identical answer. Okay, so, we get a giant booyah, or if you prefer, and I do, I prefer in, let's say, green, QED. Okay, quadrant demonstratum. Okay, in your face, punks. All right, so we did it. Okay, now, so, I mean, if you just look at this space, if we look at this, it's like, well, look at this. This was a little annoying because it had a little trig, but man, look how quick that was, and look at how annoying all this was. We stretched halfway around the page. Okay, so why would we use this method? And I'll tell you why, or at least one very obvious reason why, is that right now we just have two ropes. What happens when we've got 3 ropes or 4 ropes or 5 ropes, or maybe not all the ropes? But you can imagine how complicated the trig gets if we've got an A, and then there's a B, and then there's a C, then there's a D, and there's an E. Okay, and then your resultant vector looks like this. Okay, you can see how that would get a little bit difficult. Okay, that's the number one reason why we would want to do this method over here. Okay, the other thing is, like, if you were coding this into a computer, this method is really easy to code. This method, not so much. Okay, not so much. Okay, you're going to need to know both. I mean, there's just going to be times when you need to be able to do the trig. But probably what's going to happen is in your time as an engineer, you're ultimately going to become more comfortable with this one, just because it's going to show up more often. Okay. Now, I did want to kind of, before we moved on from this, I wanted to talk about what it was that we did here, because, there's this, I created this massive formula right here. Okay, and I do not want you to try to memorize this formula or anything ridiculous like that. But I just want to kind of show you where that came from with respect to the quote-unquote typical problem. Let's see, I wonder if I can't grab the typical, well, I can grab the typical problem, but it grabs everything else. Okay, so let's just go up here, and I'll just kind of sketch out kind of what we did, okay, conceptually. So what we did here is I had one thing going this way, and it was 10 newtons. And then I had another one going this way, that was 7 newtons. And I said, you know what, let's break this thing down. And what I want to do is I want to just think about the components. So I want to add, so what I'm going to do is I'm going to think about this component and this component of the 10 newtoner. So this is 10 newtons. Let's zoom in a little bit. 10 newtons cosine of this angle, theta. Okay, and this one right here is 10 newtons sine of that angle. So then, well, we're going to delete that 10 because it was in the way. And then we're going to consider this 7. And so I'm going to do the same thing here. So for this 7, I'm going to start here. I'm going to go this way, some bit. And then I'm going to go this way, some bit. Okay, and this is 7 newtons cosine of, what did I call it? Oh, W. No, I didn't call it W. I called it, I don't know what I called it. Alpha. Sure, alpha. Cosine of that angle, alpha. Okay, and then this one right here is 7 newtons times the sine of alpha. Okay, so what we're doing when we add these vectors is I'm taking all the different, I'm just taking the parts and I'm adding them up individually. So basically I'm saying, well, let's take these two x parts and let's combine them for one giant x part. And let's take these two y parts and combine them for one giant y part. So these are the x parts, okay? These are the y parts. Okay, and we combine them and we make a new triangle. Okay, and so the new triangle is basically this plus this in the x direction, this plus this in the y direction. Okay, so this is the y direction, this is the x direction, new triangle. Okay, and that's what we did. Okay, that was in a nutshell what all this business was. Okay, so that is the idea. So now we're going to take this one step further, and this is like my favorite step, and we're going to get into equilibrium. And what equilibrium asks is for that problem that we had drawn and we've been kind of working all day, and I love this because this is like finally something kind of simple, is we might say, okay, well, we've got this thing going off this way at an angle, you know, whatever it might be, and then we've got another one going off at this angle, and this is 7 newtons and this is 10 newtons, and we want to know, okay, what does the ground have to do to this pin to keep it from flying out? Okay, or just to keep it still. Okay, with this being 30 degrees and this being 50 degrees, and we say, so this is what's given, and we need to say required, or if you don't want it, let's not even do the ground. Let's say, what is the, you know, what does this connection right here need to do to the ring? Okay, so the force on, what would we call that force? Let's say bottom of the ring, to keep it there, okay, to keep it still, okay, because that's important, right? We want to know, what is that force? You know, what's gonna be required to keep this sucker from just flying away into space? Okay, and this is, you know, the fundamental thing of all engineering. So there's a few ways to approach this, and of course it's actually this is actually in some ways a trivial problem, but let's imagine here's my free body diagram of this ring, right? And so I'm only going to draw. So when we have a ring, we're going to assume the ring solution. Okay, let's do the free body diagram down here. Okay, I don't want to muddy things up. Let's do the free body diagram down here. Ignore all this. Okay, so we've got, here's our ring, and it's got a force on it going this way of 10 newtons. Okay, it's got a force on it going this way of 7 newtons. Okay, well, let's put some angles in there, 30 degrees. Let's put this angle in there, 50 degrees. And now we're like, okay, what are the forces? Well, obviously there's another force, so this thing would go flying off into space, right? So there's a force here, and I don't know what that force is. All right, I have no idea what that force is, right? But I know, I have a pretty good guess that the force in that ring is going to be going off this way, right? Because otherwise it seems like it's just going to fly off in the other direction, right? So the nice thing about this is, and I guess there's a lot of different ways to put this. Oh, we have to consider gravity, right? Is there a gravitational force in this ring? Okay, we could put the weight in there. Okay, that would make this problem a little bit more difficult. But for the sake of just kind of where we are right now, we're going to assume it's weightless. So what I'm going to do over here is I'm going to put an assumption, which I did not want to look like that. Okay, we'll assume weightless. Okay, because I don't want to talk about weight right now. Okay, but weight isn't really that much more difficult or anything. So here's what we're going to do. Okay, we're going to say, if this thing is still, okay, or if we're holding it in place, or any one of these words that you'll see in these any of this language that implies to you that this thing is not accelerating, what does that mean? That means that the sum of the forces in the x direction equals the mass times the acceleration in the x direction, okay, equals, well, because the acceleration equals 0. So that means the sum of the forces in the x direction equals 0. Okay. Similarly, I could say the same thing for y. I could say the sum of the forces in the y direction equals 0. Okay, it's not moving, so the forces have to balance. Okay. So if I draw this out, what that means is, so if I draw kind of my little force triangle, here's my force triangle. Right, I got a force going off this way at 10 newtons. Okay, and then I've got this one going up this way at 7 newtons. Okay, now I could draw the resultant, but I don't want to draw the resultant. What I want to draw is they all have to add up to 0. So if they're going to add up to 0, that means this is the last force. Okay, that is the force on the bottom of the ring. So I'm going to call that force on the bottom of the ring. Okay, so force on the bottom of the ring. Okay, so I'm asking for what force am I going to need to counter that 10 and that 7 at their respective angles? Well, it seems like this is, we might be able to figure this out. Okay, and the way we figure this out is we go back over here and we say, well, look, the resultant of those two looks like this, right? So therefore, FR is the opposite of the resultant, okay? Because look, the resultant, if I draw it in like white or something, the resultant is cruising along here like this, okay? To counter that exactly, I need this blue thing. I need this big blue line to do its blue best and counter it exactly, equal and opposite. Okay, that's the only way this thing is going to stay where it is. Okay, so Newton's third law, for every action there's an equal and opposite reaction. So you're pulling, or somebody, or these two ropes are pulling on this thing, up and to the right. Well, the ground, the bottom, whatever's holding on to the bottom of the ring is going to pull in the exact opposite direction. So this makes this problem nice, okay? So what it means is we're going to just kind of step up to the plate and we say, okay, well, the resultant, oh, we don't need those bars, but, why won't this just erase? It's just really just not that complicated. Yes, I know, thank you, okay. I hope you guys talk to your computers at home as well. Anyway, so here's the resultant. And the resultant was 15.5 newtons at an angle like this of 50.3 degrees. So FR, and there's a few ways to write this. One, you could say it's negative 15.5 newtons at an angle of 50.3 degrees. I think most people don't really like to get negative answers. So I would propose that you always keep it positive, okay? And we make the angle like this, and we just kind of, oh, well, that's really, really silly. I just did that so that I could erase something again. I have to fight my computer again. Okay, anyway. So we're just going to make it opposite this way, okay, 50.3 degrees. Okay, and that's it. Okay, and sometimes with the way you'll see this drawn is you'll see people do this and they'll say, oh, 50.3 degrees, and they'll write the little arrow like that, 15.5 newtons. Okay, and that's the force that you need to maintain equilibrium. So, yeah, because that way it won't accelerate. Equal and opposite. Beautiful. All right, so now we're kind of at a funny spot because, you know, I would like to get into 3D stuff, but, you know, we're at 50 minutes. So I think we're going to avoid that, especially because I want to, every day, I want to draw you a free body diagram of a problem. So let's do a free body diagram. All right, so I give you the classic physics problem of some kind of box sliding up and down an inclined plane, and I hated this problem. I hated teaching it. I hated learning it. I remember it just confused me about whether or not I had to consider, you know, one mass when thinking about the other, and all the things that were going on here. And you know, so this is the given. Okay, required. I want a free body diagram. Okay, that's what I want. Okay, and I'm just doing this to kind of keep, I want y'all, when you leave this class, to be able to draw free body diagrams like it's nobody's business. Okay, I don't even know what that means, like it's nobody's business. But, you know, let's make it nobody's business. Okay, and in this case, I want a free body diagram of M1 and M2. Okay. And, you know, and the reason that we're doing this is because one of the things that creates a problem, or at least it did for me when I was learning all this stuff, is I would look at M1 and I would say, like, does the friction on M2, and I would say, does the friction on M1 matter? Right? It seems like it does, right? And I'll tell you, it does matter, but that doesn't necessarily mean that it matters, you know, in the way that you would think, okay? And you might say the same thing about, you know, M1, like, you know, do I need to consider, say, M2, you know, do I need to worry about that? Do I need to worry about this hinge, whether or not the hinge has friction, you know, like we always solve these problems as if it's frictionless. Let's go ahead and make it frictionless, frictionless, okay, because the hinges are always frictionless in class, right? Because we live in a very nice frictionless world on our whiteboards, or in this case our blackboard. Anyway, so let's talk about it. So here's M1, okay, and we have two. Okay. So what you need to think about. We're going to assume that there's no air. Okay. Let's make an assumption. Let's do this in red. Okay. Let's make an assumption. No air. Okay. I don't want to deal with wind resistance. I don't want to deal with pressure, any of that business, okay? Which is pretty typical of physics classes. Lower level physics classes. I'm sure they have higher level ones that deal with that. Fluid mechanics, for example, my favorite. All right, so here's M1, and we want to think about the forces on it, okay? There's two different types of forces, body and surface. All right, so let's consider those. Okay, so, well, let's do this in like white or something. All right, well, there's the only body force is weight. Okay, it could be gravity or something like that, but we don't have that here. So we've got a weight going down. Okay, typically we'll draw that weight as mass 1 times gravity. Okay, so weight equals mg. All right, now we need surface forces. So basically, we need to look at, we need to replace anything touching the object or the system with the appropriate force. That's a misspelling. Okay, anyway, you know what I mean. Appropriate force. Okay, so along this bottom edge, for example, well, there's friction acting. Friction looks like, you know, a little thing like that. So usually that's written the force of friction. And there's a normal force. So the normal force is coming up from that bottom edge. It's coming like this. Okay, so that is usually written as F sub n or just n, depending on the class you took. Anything else touching the box? Well, we've got air, which I'm going to assume there's no air. Okay, no air. And then we've got the tension of this rope. Okay, the tension of the rope. Okay, so we replaced the rope with the tension. We replaced the bottom with friction and normal force, and we replaced this with, and that's everything that's touching it. Perfect. Perfect, I tell you. Okay? So that's how we draw a free body diagram. Okay, we replace everything that's touching it with forces. At some point, we'll start replacing them with moments as well. But for now, let's not worry about that. And now if I were to do M2, okay, the second mass, okay, so same idea. Here's my mass. Okay, what is do I have a body force? Yes, I have weight. I'm not, in outer space. So that's going to be M2 times G. And then the only thing touching it is this cable. So I've got a tension going up this way. Okay, whole problem. Okay, now if you wanted to solve this, this becomes relatively easy at this point. Okay, so if you wanted to know, for example, if this thing were going up, if like M1 or M2 were going up or down, you would look at this and you would determine, you'd have to, you could only determine if it was accelerating upwards or downwards, but you would sum the forces here and see whether or not it was greater than or less than 0 to determine the direction. Okay, noting that T, in this case, depends on, T over here depends on this friction, this force of friction here. Okay, so over here, friction matters because friction matters to T. Okay, so the friction on the bottom of this thing, will affect this T, which is the same as that T, which therefore will affect, how much this thing goes up or down. Okay, the last thing that we could do for a free body diagram, if we wanted to, is we do the hinge itself. Okay, and this would be a great problem for this class. So if I just said the hinge, well, here's my hinge. Okay, well, let's go look at it, right? It's frictionless. Okay, but we have to replace a force here, a force here. These are the things touching it. And there's a force coming in right here. Okay, and then there's the weight. So we need to account for all of those things over here. So we're going to have a weight going down. So that's, I guess, the mass of the hinge times gravity. There is a tension force here. There's that same tension force here. Okay, and then there's something holding it in place right here. And we don't know anything about its direction. So this is kind of one last thing to learn today, is that if you don't know anything about its direction, we could draw a force like this, just like F, and then with an unknown angle, alpha equals who knows, F equals who knows, right? That is not typically how we solve these in this class. What we're going to do way more often is if you don't know a force, you're going to draw two forces. Okay, and in this case, this little attachment is capable of pushing to the x direction, and it is capable of pushing in the y direction. So if you use those two forces, if you solve for these two forces, then you can get whatever it is you want. And the nice thing is, by assuming they're positive, then if I solve for them and f of x becomes negative, that means the force is actually to the left. Okay, so we're going to get to all that, but this is just a free body diagram. I'm going to try to do one of those each week. That was 8 minutes. I'll try to do them faster. I guess if I'm just throwing them in at the end, if you're like, I know how to do a free body diagram, Wagner's wasting my time. Okay, don't watch it. You're an adult, so it's a beautiful world. All right, anyway, as always, take care of yourself, mentally, physically, and all that other stuff. And this hurricane, I don't even think it rained. So if you want to date this is Hurricane Laura when we're creating this. So anyway, take it easy, and see you guys. And that's it. Okay, bye.